Good afternoon, dignitaries. Myself is k.Hrushikesh and I'm from EEI section. Today I'm going to do my assignment to further subject engineering physics. And my topic is about dielectric polarization. At first, let me give a brief introduction to dielectric polarization. Dielectric polarization refers to the phenomenon of electric dipoles being performed in a material when it is subjected to an electric field. It occurs when the electric field causes the charges within the material to become displaced from their equilibrium positions. This displacement of charges gives rise to the polarization of the material. In the figure, we can see how the electrons and protons or positive charges or negative charges are arranged. Polarization of an dielectric in an electric field, capital E, gives rise to thin layers of bound charges on the dielectric surfaces, creating surface charge densities plus sigma n minus sigma I. And let's see what are electric dipoles and polarization. An electric dipole consists of two equal and opposite charges separated by a small distance. When an electric field is applied, the dipole experiences a torque that aligns it with the field. The net effect of the aligned dipoles within a dielectric material is the creation of induced dipole moment leading to polarization. Here you can see an electric dipole consists of two equal and opposite charges separated by a distance d. Let us see what are types of dielectric polarization. Electric polarization occurs in non-conductive materials where electrons are displaced from their equilibrium positions. Ionic polarization occurs in materials with ionic bonds where positive and negative ions are displaced in opposite direction. Orientation polarization occurs in materials with permanent dipoles like polar molecules aligning themselves with the electric field. Let us see what is dielectric constant. The dielectric constant, also known as the relative permittivity, is measure of how well a material can store electric energy in an electric field. It represents the ratio of the electric field in vacuum to the electric field in the material. Dielectrics with higher dielectric constants have higher polarizabilities and can store more electrical energy. Let us see what are the factors affecting dielectric polarizability. The nature of the dielectric materials plays a crucial role in determining its polarizability. The presence of permanent dipoles, ionic bonds, and high electron mobility contributes to higher polarizability. Temperature and frequency of the applied electric field can also affect the polarizability of dielectric materials. Molecular polarizability refers to the ability of an individual molecules to become polarized in an electric field. It is determined by the size, shape, and electronic structure of the molecule. Polarizability is quantified by the polarizability tensor, which describes how the electron cloud of a molecule responds to an external electric field. Macroscopic polarizability refers to the overall polarizability of bulk materials, taking into account the arrangement and interactions of its constituent molecules. It is related to the molecular polarizability and density of the material. The macroscopic polarizability is an important parameter in understanding the behavior of dielectric materials in various applications. Dielectric materials and their polarization properties plays a vital role in various technological applications. Capacitors utilize dielectric polarization to store electric energy. Dielectric materials are used in insulation, electrical devices, sensors, and communication systems. Dielectric polarization allows for the storage of electrical energy in capacitors. The energy stored is proportional to the square of the electric field and the dielectric constant of that material. Higher dielectric polarizability enables greater energy storage capacity in capacitors. Dielectric polarization and polarizability are fundamental concepts in understanding the behavior of dielectric materials. They play a crucial role in various technological applications, ranging from energy storage to communication systems. Further research and advancements in dielectric materials can lead to improved performance and efficiency in various fields. Thank you.